Good morning. Hope everyone is excited to be here. So on behalf of the entire steering committee, MIT IEEE Club, and the IEEE Boston section, it is my great honor to welcome you all to the second ever MIT IEEE Undergraduate Research Technology Conference. I'm Alice Sun. I am the chair of this conference, and we are all so delighted to have you guys here with us for this weekend. This conference is a rare chance for research to spotlight undergraduates and really showcase all of the great work that you guys are doing. This weekend, we're going to be featuring novel research findings in all sorts of exciting fields, and all of them with the ultimate goal of advancing technology for humanity. This conference is also unique because of who it brings together. Among us here, we have students, professors, industry leaders, engineers, and scientists. We have people from a whole spectrum of fields, and people from all across the country and even all across the globe. But we all share in one thing, and I think that that's the theme of this conference, MIT, meets innovative technology. And we're really hoping that this weekend, this conference will be a way for you guys to meet and gather with like-minded people so that you can discuss and share new ideas in innovative technology. So I really encourage you all, whether you're here to present or not, to reach out and talk to new people, make new friends, make connections, and see if you come up with any new ideas for the future. At this point, we're going to kick off the conference with 2 talks. But before we do that, I just want to remind everyone that at the end of the conference, we're going to be handing out awards for the top paper presentation and top poster presentation. And the judges are going to be all of you guys. So as you're going to these presentations and listening in or looking at the posters, do so with critical mindset so that you can decide which one you want to vote for at the end. And we'll hand out the award at the final closing ceremony. So at this point, it is my great pleasure to introduce Matteo Riondato. I asked him how to pronounce his name just before this. And he's our first speaker. He is a research scientist at 2 Sigma Investments in New York City, and he's also a visiting professor of computer science at Brown University. He does research in algorithmic data science, and if you guys don't really know what that is, don't worry, he is about to tell us all. So without further ado, let's welcome Matteo and hear what he has to say about his exciting field of research.
Thank you all. Good morning. It's a great pleasure to be here to speak to young, brilliant minds like yours. It's very exciting that IEEE and MIT came together to organize a conference for young researchers like yourself. I used to be that too at some point. Now I'm a little further up in my career. Alice almost said everything about me. So my research area is algorithmic data science, and this is what I'm going to talk about today. Here you also have my coordinates, and feel free to reach out about anything about, 2 Sigma or research or whatever, career advice, or anything that you may think that I can help you with, or really just comments about my talk or whatever. I really have to say just 2 things about 2 Sigma. 2 Sigma is a technology company in New York City we apply the scientific methods and especially data science to the world of investments. But it's really a technology company. We mostly hire from the STEM fields, and it's an incredibly exciting place to work and to learn and to grow as researcher and as human beings. And specifically, I'm in the labs group, which does basic scientific research, and this is what I'm going to talk about today. All right. So we're all scientists really here, more or less. So let's start with the way that we usually do science by posing a conjecture. And my conjecture is that no matter what science you pick, let's call it X, the way that we are going to do science, that science X in the 21st century is going to be by somewhat applying data science to X, plus some, term that I cannot model with this, that cannot capture with this model. And there is a lot of evidence that this is going to be the case because, we have seen in the past maybe 15, 20 years, a number of disciplines that are called computational X. For example, probably the most famous is computational biology, which managed to achieve many, many successes. And there's computational finance, there is even computational social sciences now, and so on. And these are all ideas about applying computational tools and the ideas from the scientific methods, or from the scientific methods plus computation to many, many scientific areas. And we are seeing also a development in computational humanities and stuff like that were probably impossible to imagine just a few years back. But actually, the impact of data science on science can be much larger than just an application of tools to the science. And continuing with my conjecture, I really believe that data science can have an impact on science similar to the impact that statistics had on the science of the 20th century. If you think about it, almost all new scientific results are basically presented as probabilistic results. Even when the discovery of the Higgs boson was announced, it came with a p-value, which is basically how likely was it that we found this by chance rather than to actually observe a real phenomenon. So this is a probabilistic statement that comes from statistics, basically. And I believe that data science can have a similar impact on the science of the 21st century in the sense that it will really allow us to ask new questions because we are going to be collecting new data. And this is going to be possible by things like wearable technology that one of you was telling me earlier, to new methods to measure our cities, the way that the way our cities behave, the way that our cities generate data. There are so many aspects of our society that we didn't think were data generating processes before, and in the 21st century we're going to see as the core of data generation processes so that we are going to be able to develop new methods for understanding society in the 21st century. And in order to understand society, we're going to be needed new computational tools, new statistical tools, and put them together to achieve a better understanding of society, of human life, and of our universe as well. Right, so data science. So first there's data, and I don't really care whether your data is big or small or fast or slow or whatever. We have heard for, probably from 2005 to 2012, people were really pushing this word big data. And, it's kind of the worst expression people could come up with because really, big data doesn't mean really anything. We don't care about big data. We really care about, new data, modern data, data that has a lot of discrepancy within itself, is very heterogeneous. Maybe it comes fast, maybe it comes slow. There are whole disciplines where actually collecting data is very expensive. Think about, collecting tissue samples from patients that have some rare form of cancer. Well, first I have to find the patients, and then I have to collect the sample, and so on. So the idea that there is going to be big data in those disciplines is kind of ridiculous. What is important, though, is that no matter what data we have, no matter where the data comes from, whether it's from sensors that I put on traffic light to measure pollution, to measure light pollution, for example, also to skin samples from cancer patients, from the data that the NASA announced a new telescope that is just completed to be built and is going to be the largest telescope ever or something. and this is going to be collecting so much data. So it doesn't really matter what data you're going to be having. The important part is that we are going to be able to extract information from it. And this is what data science is about. So data comes first, or maybe science comes first, in the sense that we always start from a scientific question, in some sense, and then following the scientific method, we develop an experiment. The experiment allows us to collect data, and then we need to interpret this data. And this is, data science enables us to analyze this data. So why do we actually need the word science in data science if the scientific method has always been about collecting data and analyze it? Well, you may have heard the joke that if you need to add the word science to something, that thing is not really a science. Take computer science, for example. But really, the idea is that even when we develop methods for data science, we really need to be following the scientific method itself to understand whether those methods are actually the best one for the problem at hand. We need to run experiments to evaluate the performances of the methods we develop. We need to go back and formulate a different hypothesis about how we can develop better algorithms for the problem that we are looking at, and so on. So if you want, it's a science because in order to push it forward, we need to use the scientific methods on data science itself. So let me give you my recipe for data science now, and it's a bit of everything. So obviously we start, as I said, from a scientific question. There is some phenomena that we want to study and understand. And so we create an experiment, and then we start collecting data, and so on. So at this point, I have my data, but I need to understand, first of all, how should I represent this data? Is this a graph? Is this a time series? Is this something else? Is this just a sequence of strings or whatever? And depending on your domain, you may have different representation. Now, once I've chosen a representation, I need to be able to store this data, retrieve it, indexing, and need database systems, basically. And I need to be able to really manage this data, trace back how I generated this data, and so on. And these are all the problems that people in database, information retrieval, and partially data mining also are involved in. After I have this data, I can start making some modeling of my data, of my process, based on my domain expertise or the domain expertise of the scientists that are involved in the process. For example, is my time series stationary? Is my graph a power law graph? Does it exhibit other properties that I may be interested in, or that allows me to restrict the kind of methods that then I'm going to use to analyze the data? Because one great thing about computer science, data mining, and the field of information retrieval and statistics is that we really developed a lot of methods, and now it's a problem of choosing the right one. And so modeling is especially important to understand which methods will fit the best. And this is where your computational thinking and your knowledge of algorithms comes into play, so that you're going to be able to use the right method for the right data and the right problems. And all of these aspects that are definitely more computer science aspects are going to be are tied together with by domain expertise. Okay, someone your your favorite biologist or your favorite astronomer has domain knowledge of the problem and can help you with the data representation, the mathematical or statistical modeling, and perhaps even the choice of different algorithms or thinking about your data in a computational way. And you put all these elements together, and then you do your science. So the way that really this element interacts, and I'm showing you a representation of my favorite kind of tool, which is a graph. It's kind of this. So we have the domain expertise that comes from somewhere externally, or maybe your own. But usually, we should more and more see computer science and data science as a science that is at the service of other science, that enables other sciences to do their job and to better understand the world around us and inside us and whatever else. So we have domain expertise. These influence the modeling, the management, and the algorithms that we are going to use on our data. At the same time, also the modeling influence these other two, which together influence each other. So it's a bit of, there isn't much communication back from the algorithms to the domain expertise, except with the part that, after we run our algorithms, we're going to learn better, or we're going to learn something about our data or our phenomena that we are interested in, and so we increase the domain expertise. So the part that I'm more interested in, if you want, or the part that I'm going to talk about now, and it's the part that really algorithmic data science is about, is the part that deals with the management of data and the algorithms to analyze this data, okay? And you obviously need some domain expertise, at least in the part that, you need to know your algorithms, you need to know your database theory, you need to know your statistics in order to be able to solve these problems and to create new methods that are working well for the data that you have, for the problem that you have. Okay, so the best way that I found to describe algorithmic data science was a list, which is not really a good way to present things, but please accept my apology for that. So the way that I see algorithmic data science is really algorithms that give algorithms for data that have, for example, approximation guarantees on the quality of the results that we can get from the data, that are for specific kind of data representations, such as data streams or time series or graphs, that can be algorithms that can be used to perform statistical testing, that can help you efficiently run multiple hypothesis tests in parallel and make sure that all your p-values are corrected for the fact that you're testing multiple hypotheses, algorithms that can leverage modern distributed systems such as Spark and MapReduce, and algorithms that use sampling for to either speed up the execution of algorithms by only looking at a small portion of the data, or see the data as a sample from which you have to infer something about the process that you're studying. And I can go on, and one may say that this is what theory of computer science and the fields of algorithm has been doing for the past 40 years, probably. But my claim, which is actually the title of this talk, is that algorithmic data science is actually much more than just theory. Theory is not sufficient because theory is often too much obsessed with lowering your polynomial exponent of your computational complexity of your algorithm from n to the 2.37 to n to the 2.36, and no one really cares about that, because if n is 10 billion data points, it doesn't really matter whether you're lowering that little. A polynomial time algorithm may already be too much for the amount of data that we often find in algorithmic data science, in problems from the scientific domain. So what you really care about may be sublinear algorithms that can run faster than they don't actually have to look at the whole input, or that can somehow understand from the data how to adapt to the runtime and then inner working so that they can execute as fast as possible. And this is somehow a field that theory has not studied properly, and to me is the area of computer science that algorithmic data science is really trying to fill. So in some sense, approximately, and this is a change from actually my talk title, theory, so algorithmic data science is made up of both theory and practice somehow, summed together, in the sense that, okay, we make a theory, we develop an algorithm, but then we really need to be able to implement it and test it on the real data, on the problem that we have at hand. And based on the information, both on the runtime, on the accuracy, on the statistical power of my test, and so on, that I obtain from my real data, I should go back to my theory to improve my algorithm. And this is a continuous cycle that allows me to extract the best information out of the data and at the same time develop the most powerful algorithm possible. But actually, this combination of theory and practice is much more than just a sum. So the way that I like to think about it is more of a multiplicative effect of theory and practice on theory that allows me to really get the best out of my data, which is really the ultimate goal of data science, to get the most information out of the data, possibly in the most fast way possible. And so this is what my point of view about algorithmic data science. So let me give you an example of how this can actually happen. And this is partially taken from my own research. So we start from a scientific question, for example, finding the relevant web pages on the web. You may have heard that there are companies that do this. Or finding influential participants in a social network, or finding key proteins in a network, and so on. So we have this scientific question. It's a very natural question to ask. And the most natural representation of your data is going to be as a graph, like the one that is shown here. And now that we have our data representation, we ask our modeling question. How do I actually measure what the important nodes are in a graph? Importance is, at this point, is not a mathematically defined quantity. Okay? So what do I need? I need a function that goes from the set of vertices V to the positive reals, which expresses for each node its importance, with the idea that the higher is this function, the more importance is going to be the vertex. These are the functions like these are called centrality measures, and PageRank, for example, can be seen. The score that PageRank computes on the web pages of the web can be seen as a centrality measure. There are many others. For example, the degree of a node can be seen as a centrality measure. The one that I like to work with is called betweenness centrality, and it works as follows. Suppose again we go back to modeling and to use our domain knowledge, and we assume that somehow we have this node, this graph, and every node wants to communicate with every other node, and the communication will progresses along the shortest path. Okay, so I hope you are all familiar with the concept of a shortest path. It's the lowest, if we have an unweighted graph, is the smallest amount of edges that I have to traverse to get from node A to node B. And the idea here about in betweenness centrality is that the importance of a node is based on how many shortest path does a node belongs to. If there are many shortest paths that go through that node, it means that that node is very fundamental for forwarding communication around the network. And so we can formally define betweenness centrality that I'm going to denote with Bx, and without going to the formula, which we don't need to today. It's basically the weighted fraction of the shortest path that go along to, that go through a node among all the shortest paths in the network. So intuitively, what I need to know is I need to know all the shortest paths in the network, and for each node, how many shortest paths go through that node, and then I'm going to be able to compute the betweenness centrality of a node. But so, for example, in this graph, we have that the nodes B and G are those with highest betweenness centrality. Actually, G is even higher than B, because if you think about it, B and G basically enable the two sides of the network to communicate, basically. So all the shortest path between the left side and the right side I have to go through either B and G. Okay, so now that we have this problem formulated, pretty mathematically, we ask how do we actually compute all the betweenness centrality of our graph. And there is an algorithm, it's called Brande's algorithm, which is decently famous, I would say. And the idea is that for each vertex S in the graph, you basically run Dijkstra algorithm or BFS to compute the shortest path directed at cyclic graph from that node, and then you're going to start backtracking from the farthest away node in the DAG towards your source. And while you walk, you basically increment your computation of the betweenness centrality of the graph. So, for example, if the source is 1, in this case, we first build our shortest path, SP DAG, and then starting from the farthest away node that is not a leaf, I guess, we start backtracking and incrementing the betweenness centrality of the nodes that we traverse. So if we go to compute the time complexity of this algorithm, we have that you need to run n Dijkstra's algorithm, the n Dijkstra's execution, which each of them takes. Suppose that we are in an unweighted graph, so it's like BFS, so it's m plus n log n. And then we need to do backwards walk. Each of them will traverse at most n nodes. And so our complexity is the one shown up here, which if you think about it, it's really too much to be sensible, even for relatively small networks with, say, tens of thousands of nodes. So we need to somehow get, things like Facebook and Google want to run these on much larger networks than tens of thousands of nodes. So can we do it faster? Well, we go back to modeling and we ask and we find out that actually we really only need the high-quality approximation because we really just need to understand more or less what are the most important nodes in the network. And so we define formally a concept of approximation. Don't be scared by probabilities. They are fun. And so what we have is that our user is going to give us some parameters epsilon and delta. We can define an epsilon delta approximation as a set of approximation for the betweenness centrality of each node, so that each, with probability at least 1 minus delta, all my estimations are within some error epsilon from the real value, and so on. And so what I obtain is uniform probabilistic guarantees, which is great because it means that I have good confidence on all my estimations. And now I obviously go back to my algorithmic question, how do I actually obtain an epsilon delta approximation? So instead of running over all the nodes in the network, I'm going to just choose some of them at random and run on those. At this point, we go back, we have the theory question on how many samples do we actually need to compute this approximation. And you can think that the more samples I get, the better I will do, but how do I trade off? How many do we actually need? And this is where the theory part comes into play. And you can use very basic stuff like the Hoeffding bound and the union bound, for example, which you may learn about in any randomized algorithms class, and you learn that you need a number of samples that somehow depends on epsilon and delta and on the number of nodes in the network, which is good, except that then we run experiments. So we went to practice and we checked, is this really, I mean, do we really need this number, or is a smaller number sufficient? And it turns out that, it's well known that the Hoeffding bound and moreover the union bound are very loose bounds. So many fewer samples were actually needed than what was suggested by the bound. Moreover, even looking at the bound from a theoretical point of view, we didn't really like the fact that the bound was dependent only on the size of the graph, so that it was not using at all the edge structure of the graph, which is, if you want, what really drives the betweenness centrality of the nodes. So we went back to the theory. And we used something that's called the Vapnik-Chervonenkis dimension, or VC dimension, which was developed for something completely different. This is another aspect of algorithmic data science. Go study the theory, see whether, doesn't matter what it was developed for, take it to a different field, to a different problem, adapt it, and so on. And we really twisted it because this thing was developed to evaluate supervised learning classifiers, so think about classification problems, and we actually showed that it can be used for a graph mining problem. And it's a beautiful, there's a beautiful theory behind it. It's called statistical learning theory, and it's really, really elegant, and it's incredibly, incredibly practical. And what we were able to prove was that you actually only need a sample that depends on the diameter of G instead of the number of nodes, which is great, because social network, for example, may have a lot of nodes, but they always have very small diameters. You may have heard of the 6 degrees of separation, but actually on Facebook, most users are separated by even fewer hops. So we basically decrease the sample size exponentially by just, evaluating our theory on real data and then go back to the theory and so on. So this was great, but we ran more experiments and we saw that this was already too much. And also from a theoretical point of view, not all graphs with the same diameter are equally hard. So what can we do? Well, we went back to theory, we studied more, we looked for more powerful results, we see whether we can learn how hard the graph was to approximate somehow with different tools. And this is actually our latest result. It's just to, instead of computing first a sample size and then start sampling, which is what the previous results were about, let's just start sampling and then somehow use the information that we get to understand when to stop. And it gets a little messy here, so I'm not going to talk about what's in this bound. But it turns out that, again, we run experiments, and this is getting very close to what the practice suggests, to what the real number of samples seems to be to get an epsilon delta approximation. On the other side, yes, proving stuff is becoming a little bit more complex. There isn't much intuition in the quantities that comes into play in the formula here. But it was very satisfying to prove, which is one of the reasons why I like to do research. Proving bounds is fun, and proving theorems gives you a lot of satisfaction because you're the first to know something that nobody else knows. And anyway, so it's fun. And then again, we went even further. We mixed theory and practice even more. We said, oh, we really don't care about theoretical elegance at all, but we still want to maintain correctness and get our approximation. So we came up with this crazy, almost convex optimization problem. We want to solve it. There is really no elegance at all here, but it works. It's theoretically correct, and it gives amazing results in practice, which is really what algorithmic data science is about. Correctness plus efficiency. You lose elegance, fine. Let's have the theoreticians play with elegance, and let's us play with data. And if you think about it, if you want to be a data science, you really need to get your hands dirty with data. To be an algorithmic data scientist, you also need to get dirty with data and the theory part. You need to start opening the proofs of all theorems that you're going to use and see whether you can tune them up to be more practical, to give less intuition but be more powerful, and so on, to get the most out of your data. And we work on many other problems. We, again, mixed different kind of theory. The last one is another beautiful theory, semi-ready regularity, and can be used to analyze graphs. Non-IEEE sampling and more VC dimension and so on. And we saw again and again this pattern of going to theory, repeat apart, make it more practical by improving each bound and losing the elegance and getting great results in practice. So to conclude, I really suggest that no matter what your field is, you should embrace data science, and no matter what your field is, there's going to be a theory, whether you're database or programming languages people or information retrieval or theory people. You should take the theory and combine it with practice to get the best out of the data so that we can help science go forward. Thank you. I'm open for questions. I don't know if we have time or anything.
Yeah. Any questions?
Two Sigma has internships, obviously. You can write to me without any problem. Sadly, I have to leave out of here right now because I'm actually going to my wedding. Yeah. So, yeah, that was kind of hilarious. Last week, I noticed that I fixed these two things the same day. Well, you know, whatever. I can handle this. Yes, so Two Sigma has a lot of internships, so just write to me and then put in touch with the right people. Thank you.
All right. Thank you so much, Matteo, for that talk. I'm actually really interested in data science myself, so I personally found that really interesting. And a huge congratulations. Enjoy the wedding. I'm very honored that you decided to come despite that. So next, we're going to be welcoming Ali Abedi. He is a professor at the University of Maine in electrical and computer engineering. He has received numerous awards from IEEE and NASA. He's published over 80 papers in IEEE journals and conferences. And he works really closely with IEEE on committees. And so we are very excited to have him here with us today.
Thanks very much for having me here. Thank you, everybody, for waking up so early to come to my lecture. Usually, my own students don't come this early to my classes. They always tell, please teach after 11. So what I'm going to talk about today is about one of the projects I've been working on the past few years basically in the area of wireless leak detection for different kind of pressurized modules, right? So, of course, the application is not just depending on a space application. It can be the propane tank in your home. It can be your water delivery system, sewer system. It can be oil and gas platform. But NASA pays us, so we do the work for space, right? So before I start, just want to show you where we are. So University of Maine has several different campuses, 7 campuses. We are kind of in the middle of Maine, right here in the down east, close to Bangor area, a small town called Orono. It's like Toronto without the T's. We have 12,000 students. We award multiple different PhD, master's, undergraduate programs. We have everything except medical, pretty much. So, and this is my lab called Wireless Sensing Lab. It's basically a 4,000 square feet metal box, right? And the reason I built this a few years ago was I received an inflatable structure from NASA. We had a big project a few years ago, and they sent me this 42-foot donut that it didn't fit into my other lab, and there was no other room on campus I could fit this in. So we had to get a piece of parking lot and build a new building for it. So this is the first inflatable lunar habitat module that was built by NASA Johnson Space Center. They send that to us in bits and pieces. 20 to 30 undergraduate students assembled it together for us without any instructions in a couple months. I don't know how they figured this out, but just imagine you have to build this structure like a skeleton of PVC pipes and wooden flooring, and then put some fabric around it and inflate it so it all pops up. So what we did, we instrumented this through multiple different projects for detecting impact, mainly because of micrometeorology and space debris impact, if things like that go to Moon or Mars. We worked on monitoring the shape and structural integrity of this, and also we worked on leak detection recently. We have been also working on some augmented reality, virtual reality sort of models, so we can train astronauts. We put the helmets on their head, and they can kind of walk inside the habitat and imagine there are things there that they actually don't exist. So I show you a very short video that some of my students prepared. So I can get that to work. So this basically shows the view of a virtual reality model we have, and you can actually put a helmet on your head and walk inside the habitat while you are actually there. Or you can start changing different equipment there. See here, there are some plants, and on the wall you will see different equipment kind of appearing and changing. So NASA is interested to kind of outfit the habitat without actually paying anything, right? So this is the way to go. We can also study different aspects of propagation and sensing as we go through this whole project. Here is a view of inside the habitat. We work on some other models, smaller models first, like a yellow structure on top was built by ILC company. This is the company who actually built the original Apollo suits back in the day. We worked with another company called TRL. They designed another module, but these three pictures kind of on the lower part of the slides, and this one, these are inside the habitat. So we instrumented with hundreds of sensors. They all send data. They all go to a base station. It's live online. So we have an iPad app. You can actually look at the three-dimensional heat map of those sensor values, right? So it's a visualized version of kind of looking at habitat. Anybody can guess what is this picture about? Yeah, I've seen this before. Yes, that's in there, but there is more. Can you see anything more than satellites in there?
There's also a ring around one of the edges, on the left side.
So you can technically, call everything that rotates around the Earth a satellite, right? Some of them are man-made satellites. Some of them are just a space debris. Some of them are like first stage rockets, or some of them are dead satellites. So there are tons of space debris around the Earth. And what happens is that if you put something up there, it's going to hit your structure. So we'll see those holes there. There's hypersonic bits and pieces that will just fly through space. So if you have seen the movie Gravity, that's real. So you have to be very careful. There are over 16,000 objects that are actively being tracked around the orbit of Earth at different levels. So you can steer International Space Station slightly to kind of avoid things that are coming in. And in future, if you want to leave Earth and go anywhere else, you have to kind of dodge all these different things. So that's a serious problem. They have very high speed, and when they hit the station or any other space vehicle, they're going to make a mark. Either they dent it or they make a hole. So here are some lists of accidents that happened since early 70s. because of leak. So you will see here from 70s all the way up to this year, we had issues with leak. Air leak, fuel leak, ammonia leak, different kind of leaks. And this is the problem we are trying to solve. We are trying to figure out if there is a leak, and if there is a leak, then where it is and what material has had penetration. Currently, believe it or not, there is no automated leak detection system on a space station. So sorry to say this to those who has aspiration to become astronauts, but you are in good hands. There is an air pressure sensor there. So if the air pressure drops, they have a handheld ultrasonic boom that they take and they put on the wall and kind of scan, and they try to figure out where's the leak. It's like when you call a plumber, right, to come to your home. But there is a graph at NASA that is basically tells you, depending on the size of the leak, how long you have before you have to evacuate. And some of those times are like 10 minutes, 5 minutes, or 20 minutes, depending on the size of leak. So that kind of motivated us to create an automatic system which is not going to need a scanning by hand. So we will put this box over there inside the space station. It listens for leaks and tells them where is the location of the leak. So I'm going to talk about leak detection. So that's basically you create a hypothesis and say if there is a leak or there is no leak, you calculate conditional probabilities, log-log ratios, things like that, and try to figure out if there is a leak or not. Once you found there is a leak, then you need to know how to localize it. And once you localize it, you need to know what kind of material is leaking. So those multiple layers of a space vehicle. So we call that leak classification. So I try to kind of touch on all these different things. So our measure of the leak is based on the ultrasonic waves that will come to us. If you imagine you have this pressurized vessel. Inside, there is atmospheric air pressure. Outside is vacuum. So you have a small puncture. The sound, the air will escape at a speed of sound or sometimes faster than a speed of sound. You imagine that that's not going to propagate any sound inside the vehicle. It's all going to go out, right? But because of that high-speed air escape, the edges of the leak will start to vibrate. So there will be an ultrasonic wave actually propagating inside the vehicle. And that's what we are looking for. We are looking for that ultrasonic wave that comes in. We have 3 different boxes which are shown here as sensor arrays. Each box has several sensor arrays. So each sensor array has like 2 sensors. And basically, this is the main part of triangulation theory. So you get a leak coming like from this angle to me. I have 2 sensors. This one will hear this leak much faster than this one. As long as you have a very precise way of measuring the phase of these 2 signals, you can find the angle, right? And then if you have 2 of these, you can get 2 lines intersecting each other. So you can say, okay, the leak is there. But if you remember your trigonometry, you want to solve those sine, cosine equations, and you always get 2 answers. You say either a leak is over there or is over there. So we put just a 3rd box to resolve this dispute and then tell which one is the correct one. But the reality of building a hardware as an electrical engineer in a lab, whether you're an undergraduate researcher or a graduate researcher, is that when you build it and you have all this elegant theory, you realize there is a lot of difference between theory and practice. Here is the red dot in the middle of the graph, shows the true location of the leak. You build this device, run it thousands of times, and every single time you get a different answer. It's a disappointment, right? So you can't really fly this to space or do anything. So that's where the power of statistics and Bayesian inference, Kalman filtering, signal processing comes in. So we do lots of those things. And basically, this will help you narrow down to those black dots which have higher conditional probability of being leak. We start with cutting the plane into 4 different quadrants, calculate every conditional probability of all these leaks, and then add them up. Then you can say which quadrant is the most likely quadrant to have the leak in it. Once you made that decision, you continue this one more time for that quadrant and do this again and again until either you're tired or you're satisfied, right? The reason we did this approach, the iterative approach, is because I always ask my NASA program directors that, what is your desired accuracy? And you know what they say? The best you can do, right? And I tell them, okay, give me like $10 million, I do that for you. And say, no, we only have like $1 million. And I say, okay, so we cannot really create these very expensive, big, huge, bulky device to give you the final answer. Instead, we created a very small, simple, low-cost device. And in fact, we didn't even build any microprocessor board. We just used Arduino boards, if you heard of it. And we created a PCB, which is like a shield. It sits on top of Arduino board and connects to our sensor. So the hardware is very simple. But I let them decide how many times they want to run this. The more they run it, they can get better accuracy. So here's the block diagram of the system that we have. So you'll see on your left-hand side here, all the ultrasonic array of sensors. We have 3 pairs. In the middle, that gray box, which doesn't look that gray up there, is the multiplexer and external ADC and the filtering and everything. So basically, the reason we do this instead of running 3 different streams of data in parallel is that no matter how hard you try to build 3 filters and amplifiers exactly the same way, they are not going to be exactly the same way. And that's where you lose that 2-sensor phase difference if the amplification and filtering has very slight difference. So what actually some of our students in the lab proposed was that we should use a multiplexer, get the data from all these 3 sensors, pass them through the same signal amplification and conditioning, so this way we are not distorting the signal. So we are basically sacrificing a speed for accuracy, right? So that's the trade-off we play. And the system, as you realize, has its own battery, its own storage system, so we are completely self-contained. We are not going to attach to anything on board the space station, so it's all self-contained system. Here is some specifications in case you want to know how big it's the system. It's like a shoebox size, as I mentioned. It's 700 grams, and it works for 28 hours if you charge it at full power for 9 hours. And it basically generates around half a gig per sensor pair. So each box will generate 1.5 gig of data. There are 3 boxes on board, so there will be almost 4.5 gigabits of data. And we sample the sensors at 3.8 million samples per second with 8-bit accuracy. Here's another view of the picture of the inside and different sides of the box. You see we have 2 redundant switches because, you know, astronauts kind of tend to kind of flow inside the space station and they might accidentally touch the box. We didn't want them to flip the switch and turn it on. So we put 2 switches, which are like rocker switch, and then on the other side there is a push button switch. So they have to do this 2 first and then push that. Otherwise, the box doesn't turn on. So the previous pictures were called like lab units. So the first prototype, these pictures are engineering units, the ones that we tested at Johnson Space Center, and we'll show you some pictures of that. You realize they're very colorful, so my students have very good taste of art. They print their own boxes. In my lab, we have a small 3D printer, so they play around with different designs and different colors. So before I show you a little bit more pictures, I just want to give you an overview of the software. So basically what happens is that the leak source emits some ultrasonic waves. The MEMS sensors will sample it. Everything is calculated and saved into a SD card. The astronauts will take the SD card out, put it in their own laptop, beam the data down, and then we'll get the data and pass it through our Kalman filtering, tree search algorithm, etc., to figure out where is the location of the leak. This is a ground testing setup in the lab. So you may have been wondering so far, how did we simulate a leak in the lab, right? So we looked at the previous data we collected from leaks. We have also a test bed that we can punch holes in it and listen. But once we did that, we got some idea of what kind of signal spectrum we are looking for. So in the first test we were doing in the lab, it was like a tabletop test. We had an ultrasonic speaker connected to a function generator, and we created a simulated wave for the leak. And you see all these purple dots up there. Those are all possible location of the leak. We run multiple different algorithms, and as you pass the data through all this filtering and Bayesian inference algorithm, you see that all those purple dots kind of concentrate into other smaller colorful triangles or inverted triangles, which are getting very close to that red square, which is the true location of the leak. So you can get as close as you want. So these are the ground testing that happened in my lab. And then sent the students last April to NASA Johnson Space Center in Houston. There is the ISS mock module there. We wanted to know how the reflections and scattering and all those sorts of things works inside that module. So they took some of these boxes there. They did the tests in terms of what we are interested in. And then there's like hundreds of the tests that NASA is interested in, and we don't care really about from science point of view. But from engineering and safety point of view, they have done lots of electromagnetic interference tests, like your box, how much pressure it can tolerate. And these things have been going on for like 2 years. Every week we have conference calls with Boeing and NASA. Boeing is the prime contractor for integrating this into the SpaceX rocket. And you have to answer questions like, what is the ratio between the area of the holes you have on the box to the volume of the air inside of the box? Can you imagine why that's important? Because when you go from pressurized area to vacuum or back, if that ratio is not within a specific limit, your box is going to burst or collapse itself. They ask, what is the temperature profile of your battery when it gets charging from the beginning to end? And just imagine asking these questions are easy, but we had to run lots of tests, take lots of measurements, take videos, etc., and send it to them. And these reviews have been going on in 3 different phases for a long time. So that's the reality of flight certification. Here's the actual flight unit, the final units that we shipped to NASA Johnson Space Center back in August, which you see it looks a little bit more space grade. So it has aluminum tape on it. It has lots of other labeling, etc. And once these things go to space in early December, this is the procedure the crew will follow. So the International Space Station crew will get this from the storage, open it up, install 3 boxes, attach them to 3 pre-specified locations, turn them on, and then get the data on SD cards, put in the laptop, and send it to us. Right? So this was Lonnie, one of my graduate students, and the other one was Ken, the other graduate students. They worked on this project. As you realize, being electrical engineer or computer engineer, or in case of Ken, a computer scientist, that's not the only thing you need to know. You need to learn a little bit about mechanics and mechanical engineer. You need to take our box and test this on different conditions. So do lots of documentation. So that kind of gives you a big picture overview of what it takes to take something to space. This video was actually shot by Discovery Channel. So this was aired this fall in Canada. And I just got permission last night from them to show like a small clip here. So you're the first group who are seeing this in a setting like that. This slide basically talks now about the time that we detected the leak, we localize it. Now we want to know what kind of material is leaking. Is it aluminum, steel, rubber, plastic? What kind of leak size do we have? A very small fraction of inch, or is it closer to like a 1/4 inch? And these different scenarios for different pressures have been simulated using that big pressurized autoclave that you realized in the previous video. So we tested the system for all these different scenarios inside this autoclave at different pressures, collected all that data, and then created a database. That database basically tells you all different scenarios for different sizes of leak and different material, etc. And once you build that with enough confidence, statistically speaking, then whenever you are actually in the real application domain inside the ISS, you get some signal, you characterize the spectral basically distribution of the signal, compare it with that leak database, and then you can figure out what kind of material and leak size and pressure do you have. So we usually start with frequency domain, right? In the time domain, as you see here, you cannot really see much. This is the time series of a 0.05-inch hole inside a steel. But when we go to frequency domain, there are multiple tools we can use. We start with the Fourier transform. Then we also looked into Hilbert-Wang transform. I'm not going to go through too much of the details, but I'm going to show you some of the results. The accuracy is not going to go up, so we very quickly abandoned that method. Then we looked into principal component analysis, kind of a subset of Fourier transform analysis, and that shows a little bit better progress. Hilbert-Wang transform, which is the red curve on the top, that shows even much better accuracy, but still we are not at the 100% accuracy. So 79% is the accuracy we can get in terms of telling you exactly what is the diameter or hole size and the material for the leak at different air pressure. But we are working on several different analysis methods to figure out what would be the best thing to do. And here I have listed a few bullet items. If you got interested to do research in these areas, we always have graduate opportunities, graduate research assistant opportunities. If you decide to work in this area, you can just send me an email with your CV. We look for master and PhD students. And also in the summertime, we always have undergraduate research opportunities as well, so I can talk about that as well. So the process we are following right now is that originally we were going to send our payload from NASA to SpaceX to be launched from Cape Canaveral in Florida. But if you have heard, in September there was a SpaceX 9 explosion, right? And luckily our payload was not on that one, we were on a SpaceX 10. But what happened was that explosion damaged the launch pad. So now they cannot launch anything from that launch pad, at least for the next few months. So I didn't watch the news, I was teaching at a time, but I came home and it was like 8 p.m. at night. I got a call from Boeing payload manager, and he told me, okay, I'm going to send you some documents. We are going to move your payload from a SpaceX 10, move it to HTV-6, which is the Japanese Space Agency rocket. And I said, why? I said, you didn't see the news? I mean, we can't really launch from there anymore. So we were the first one quickly to move to HTV-6, and next day over, everybody was scrambling to push their payloads there, and of course, there's not enough room. But we made it, so now our payload is being shipped from Texas to Japan. They are launching it to space December 6th. And hopefully, if it doesn't explode or anything bad happen, if they get it in a space station, we are on the timeline for the crew to install it and deploy it in late January, early February. And then they start sending us data. So in my lab, I have set up a ground station for ISS, so we can actually listen to the communication between Houston and ISS. We can talk to the crew in case something happens and they want to ask questions about like orientation of the box or if the battery doesn't work or things like that. And once we get that data, we are going to look at some other analysis method in addition to the HHT and FFT that I mentioned. We're going to look into wavelets, looking into singular spectrum analysis method, and trying to collect more data sets and larger data sets to figure out how we can actually enhance the accuracy of leak detection and leak classification. One other thing that we are interested to work on, and just very new idea, is that to look at topology of the leak. If the leak is like a perfect circle, or maybe it was like a hexagonal bolt that is leaking around it, or maybe it's just some puncture which kind of looks very ragged kind of edge. So how does that affect the signature? So we are trying to work with a mathematics student who knows topology, acoustic engineer who knows wave propagation, and try to kind of develop these models and theories. Here are some of the references I referred to in a few of my slides. And finally, to conclude, I just want to tell you that this kind of project is not like a one student or two student job. I had a very big research team of undergraduate students, masters, PhDs, postdocs, worked on this for almost 3 to 4 years until the theories are developed well enough so we can submit a proposal with confidence to NASA that we want to do this. And this was selected among only 5 payloads that are going to a space station this year. I also want to thank our collaborators at NASA, ISS Technology Demonstration Office at JSC, and also our other collaborators at NASA Langley and Boeing and Invocon Company, and our sponsors, NASA, Main Space Grant Consortium, Main Economic Improvement Fund, and Knowles Company, which is actually building those MEM sensors for us and integrates that into our PCBs. So here's my email. When I was a student member of IEEE, they introduced the aliases, so I got abedi@ieee.org, very small 5-letter email. If you want to get in touch with me, we'll be happy to send you more information. But we also post lots of videos and pictures on social media, on Facebook, Twitter, LinkedIn, Google+, or you can just check out our website, umain.edu/WiseNetLab. And just want to thank you for your attention and open it up to questions.
I know that right now, I'm a biomedical engineer and biomechanical engineer at the University of Texas, and I do a lot of, we've been shifting a lot to understanding more polymer chemistry, understanding 3D printing, kind of with, you saw in that video that metallics are often faulty and there's often problems in that. Have you guys put any thought to maybe, like with the new understanding of topology and quantum physics, utilizing 3D printing and superconductors to maybe optimize the printable circuit boards, the Arduinos, and be able to fill those gaps more precisely, because you could basically just analyze the whole 3D print, the exact part over top of it, and then have your superconductor, fix the problem right there on site. Is that the future direction you guys might be moving in?
That's a very good comment, actually. No, we have not worked on that area, but NASA is interested and working in that area. They have divisions at different NASA centers that are working on exactly that direction that you mentioned, and they work with multiple different universities. I think that would be the wave of future. Even thinking about all those space debris because of the metallic structures we used to put up to space, even if we can move those into some kind of degradable polymers or something like that, it not only saves the future of kind of a space debris problem, but it also saves us a lot on the cost and the fuel, because they're much lighter, much more straight to go up. So yeah, that's definitely a very good direction to go forward. And the other thing, I was glad to hear that you mentioned you work in biomedical area. So you might be interested to know that same technologies we develop here for NASA, they have applications in biomedical area. And in fact, one time that I was describing this to a neuroscientist, and she was describing to me the issues they have with PTSD and mild traumatic brain injury, things like that, I realized that there are signals there that they want to get from the brain, and they are very close to noise level. So we applied some of our algorithms to those problems. We had some success, and we filed patents. So we just got awarded a patent. We got Army grants, and now I have a startup company that we are actually creating wireless sensors for brain injury detection using NASA technology. So that's the other thing that many people don't understand, that GPS that you use every day, cell phones, like mouse of your computer, right? All those different things, it started from a space technology.
Exactly.
And the applications are just very, very wide. Thanks for the comment and
Yes,
question.
sir. Definitely.
Yes?
What's your thinking on multiple simultaneous leaks?
That's a very good question. Actually, whenever I give this talk, that question comes up every single time, right? I actually gave this talk last week at Lockheed Martin in Dallas, Texas, and 3 weeks ago in Germany at German Space Station. And every time people ask the question, and I don't know the answer, but we are working toward that. So right now with this system, we only assume one leak. So if there are 2 leaks, the answer we are going to give you is right in the middle, which is wrong. But we are trying to combine the spectrum of different leaks together. So right now, if you get 2 leaks happening at 2 different locations, we should be able to decompose those basic spectrums. And we are using some of the techniques from early 90s when the speech recognition was a hot topic of research. So we didn't have Siri at that time, but it was coming. So that technology basically can separate different spectrums together. So we are working toward that to be able to detect it. If those 2 leaks are separated enough that 2 different boxes are detecting them, then we can distinguish. But if they are too close in one box's proximity, then we still are working on that. But very good question.
You kind of answered it, because your supposition was that you're going to put it up in the space station, but there's already leaks
Yes.
in the system, so it could be 12 of them. For all you know.
Yes, that's right. So for the test we are doing right now, we can actually adjust the receiver sensitivity. So we are going to limit the box field of view to very small area. So that reduces the probability of having more leaks in there. We don't expect to get any leaks on the pressurized wall at this point, although if you look at it from outside, with the new HD cameras they have, you see all these dents. There has been some leaks that they patched actually in the past, but we are more interested in looking at the leaks around like maybe extra features that are put in there, like airlocks or maybe windows or things like that. So we can actually have a directed test happening there. But eventually, by playing with the receiver sensitivity, you can change the range you can see. Most of these problems, in fact, has been already solved in radar domain, and we just need to kind of learn from those and try to see how we can adapt it to acoustic domain, which is much more challenging. But other questions? That's a good question. So the original research we have done identified 40 kilohertz to be the central frequency. Yeah. So we thought, okay, to make a device very simple, we just maybe go 5 or 10 kilohertz on each side. Mm-hmm. But then we had some discussions with a NASA Langley scientist who actually flown an ultrasonic receiver to a space station and measured all these different kind of leak signatures and sent it down. And he told us that based on the data, the leak is actually very broadband.
Exactly.
So in order to make sure that we don't miss any specific leak in that frequency, we are actually doing a very broadband sampling of the whole signal. So we can go from like very low ultrasonic to even 100 kilohertz or more. At this point, our analysis will be focused on 40 kilohertz and surroundings, but we can certainly see if anything happens up there. But eventually, everything is going toward more broadband in communication area. Yeah. And the idea is that behind probably you have heard of the term software-defined radio, is that instead of creating a hardware which is frequency dependent and only works in this band, then tomorrow you figure out, oh, there is like another thing I want to do, I have to change the hardware. It's better to just have a very big broadband RF front end or acoustic front end, and then sample everything. Then you can do everything in software. You can tune your filters in software and everything, and we are moving into that direction.
Having that broadband perspective, wouldn't that increase the false positive rate to where you might get
absolutely it does, yeah. So that calls for more probabilistic algorithms to be able to get rid of it, and that's a very critical problem in many sensor networks. So absolutely.
Thank you, sir.
Yes. So right now, all of our equations are based on a flat planar surface. I was thinking that it may change a little bit because the curvature on the ISS wall is not certainly flat, right? So what's going to happen is that it's going to create a little bit more scattering and more kind of focus, very similar to like a waveguide property when you are working inside of a waveguide for microwave sort of technology. So here you have this curved area, and if you put your device on the wall, you are going to get more focused scattering and interference coming at you. So in fact, if you go from planar equation to a curved equation, you can calculate some correction factor to be able to compensate for that, and that basically pretty much a little bit of trigonometry, but we should definitely consider that for different curvatures when we run the data.
How would that be? I'm assuming you can't just apply some function to adjust for larger irregularities like that.
That's a good point. So basically, when we are looking at the airlocks are supposed to be airlock, right? But over years of ISS being up there, the washers and sealers around that start to age. So it's not that the whole thing is leaking, but maybe there's like one single corner is leaking. So as long as we can point out that here is where the leak is happening, they can just either repair that, or if it's serious and we say, okay, we get lots of leaks like here, and there, then they may want to just replace the whole airlock. So that's basically the point. We are trying to pinpoint very small, tiny leaks around the airlock. So it still would be a planar surface for us. Yeah.
You mentioned Arduino is used to collect the data, right? And then the data is analyzed on a PC.
Yes.
Separately. So I was wondering if you've considered using a more powerful device such as Raspberry Pi to analyze the data within the unit itself.
Yes, we actually use Raspberry Pi for our base station when we are doing the test here on Earth. The reason we are not flying Raspberry Pi is just because of its power consumption. So we could technically fly something like that, or even a more powerful processor, but there is like one more year of documentation to connect to anything on board the space station. I try to avoid Wi-Fi and power ports and everything. But eventually, if we can download the data, test it here in the lab, and figure out some ways to minimize the computational complexity of algorithms, the eventual commercial product will be a self-contained device, maybe has a Raspberry Pi or a more powerful microprocessor that can be attached to some kind of power port there, communicate with Wi-Fi, so the SD card will be eliminated. Some of these considerations was just because I didn't want to sign like thousands of extra pages of documentation. So, but that's definitely a good point, yeah.
Thank you.
Thank you. One more question here.
This question kind of comes from the, I guess, a different perspective of the polymer chemistry. You're talking about the topology. Do you think that maybe I was at a conference, a graduate talk yesterday, and they were talking about using like polymer hydrogels that were like super highly flexible, highly structured, highly rigid, but could also be integrated with circuits and have highly functional properties. Do you think that that could have a possible application in this field? Because then it could just basically be a patch over top of it that's a super strong, flexible hydrogel that also has the circuit inside of it directly, and it could just monitor right on site.
Yeah, I think that's definitely the wave of future. Flexible circuits, I think that will reduce the bulkiness of the box and everything, yes, I think they will definitely be a bit of a future. I'm not really that knowledgeable about like chemistry and polymers to say for sure, but I'm sure there are multiple different technologies that they are moving toward flexible circuit, mainly not because of the ISS, but because of the inflatable habitat structures. And inflatables, as you can imagine, can be folded into a small bit, like a small volume, and they can go to space with very low weight and low cost. So if you want to go to Mars or an asteroid or anywhere, inflatable is the name of the game. And without flexible circuits, I can't imagine any other way you can create an inflatable that actually folds and pops up without breaking all the boxes and wires. So definitely, yeah.
Great. At this point, I'm going to cut off questions. I'm sure Professor Betty will be more than happy to answer any further questions you guys have after this. So at this point, we're just going to go into a short little break. And starting at 10:30, we're going to have our first paper presentation sessions. There's going to be 3 parallel tracks, so choose whichever one you're most interested in attending. Unless you're presenting, of course, in which case you should attend the track for which you're presenting. During the break, feel free to grab food, and if you guys came in earlier to sign in and you didn't grab t-shirts yet from this year, we have those available now, so feel free to take one of those. And then in the afternoon, we're going to have another paper session starting at 1:30, and we will reconvene here at 4 o'clock for the EECS or Explore event.